use of a CDN. This is a content delivery network. And as the name implies, it is designed to provide a way to get data very efficiently from one central point to an end user. These are often set up in geographical areas. So there might be a CDN server in North America, South America, Africa, Asia, other parts of the world, and you're able to cache information at each one of these points. It takes time to get data sent from one part of the world to the other. So if you can have all of your North America users access the North American CDN, it's much faster than having them all go out to a centralized server that might be located in Europe. So if you're watching this video on YouTube or on the Professor Messer website, you're using a CDN right now. It's a way for very small or very large sites to be able to distribute their data to users all over the world and make sure that that data is as accessible and efficient as possible. For those of you that work outside of your corporate facility or perhaps do a lot of work from home, then you're probably already familiar with a virtual private network or a VPN. This allows you to connect to a remote network while sending all of this data encrypted across the network. It's a very secure way to transfer data, even across networks that would be inherently insecure, such as the public internet. VPNs often use a device called a concentrator or a head-end device to be the central connection point for all of the users who are accessing that VPN. This is often a purpose-built appliance that's designed to do high-speed encryption and decryption of network data in real time so that you can have many people being able to send secure data across the network, decrypt all of that data, send it to the inside of the network, and then reverse that process to get the response back to the user. This can be a standalone device, but very commonly we integrate this VPN concentrator function within a next-generation firewall itself. Because of the encryption and decryption process required to perform this VPN concentration, we usually will use a purpose-built appliance or piece of hardware to be able to do this. That provides very high throughput and can support hundreds or even thousands of users simultaneously. But if you have a smaller network, you may not need a purpose-built appliance, and there are many VPN concentrators that will run as software on an existing operating system. You may have to install a specialized piece of software to be able to use a manufacturer's VPN, although there is VPN software that does ship with Windows, Mac OS, and Linux operating systems so that you can connect to many different kinds of VPNs using that generic software. Not all applications are designed to run simultaneously on a network, and certainly some applications may have a higher priority to your organization than other applications. For example, there might be a real-time audio or video stream that has a higher priority than a file transfer. Because of these requirements, it's very common for network administrators to provide some type of prioritization to these applications. This is often done through a quality of service or QoS configuration. You might also refer to this as traffic shaping or packet shaping. This allows the administrator to control what type of applications can flow through their network, usually based on bandwidth usage or particular data rates. This might allow your real-time applications to have full control or access to the network and put a lower priority on other applications that may simply be transferring files. To control this quality of service, you may need to make configuration changes inside of a firewall, a router, or a switch. These devices might have a pre-built list of applications and might also allow you to add your own applications to the list. And at that point, you can decide what priority the applications might have relative to everything else that's running on the network. One of the challenges we often run into with technology is that it's very good at performing a task. And often it can perform these tasks over and over and over again without any type of human intervention. Unfortunately, this could also put a device into a state where it's performing the task over and over and over again and never finds a way to complete or end that particular task. For that reason, we've often built in different functions with our protocols so that we can recognize when a task may be going on too long and simply remove that task from the network. One common way to provide this identification is through the use of a time to live, or TTL. A time to live is effectively some type of timer. This timer may be based on the time of day, or it may be based on the number of iterations that a particular task completes. Once that timer hits 0, we can then have that task stop what it's doing, or we can drop that task from the network. There are many different cases for a time to live. One is a packet that is constantly looping between different routers. We might want to have that packet automatically dropped if that loop occurs a certain number of times. Another good example of a time to live might be to clear a cache, where we might access a website, have that website stored in a cache, and then that cache is only available for the next 60 seconds or number of minutes. When that timer hits 0, the cache is cleared, and the next time that website is accessed, you would have to go all the way out to the site to be able to bring that information back, at which point